Hello, people. I thought I'd go through the solution for this one. I know it's on your sheet. Um, yeah, but I thought it'd be a good one to look at. There's some complicated stuff here. So, as we start any torque problem, first step is always net force statement. Okay, this is in rotational and translational equilibrium, so net force is for sure zero. If we do, you know what, let me move this. I'm going to draw a separate, here's the boom. It's called a boom. All right, forces acting on the boom. We have its weight that acts at its center of mass. In this case, we have this tension acting downward. We have this tension acting this way. Let's call this T1 and T2. And then, hopefully by looking at this, you can tell, well, there has to be at least a force this way, all right? Because T1 has a left-pointing x component. So I'm going to call this NX, all right? And then I'm also going to say there's probably an NY there. All right, again, we have T2, we have MG, both pointing downward. T1, I don't know the magnitude of T1, but I'm guessing that it's not big enough to counteract both those downward forces from T2 and MG. Now, I don't even know what the question asks. Let me check that. Where are we at? Right here? No. Okay. Copy. Paste. Okay. Find the tension in the supporting cable. All right, fair enough. Well, like we said, since we don't know what T1 is, and we don't know what NX is, there's two unknowns if we were to look, if we were to look at a net force statement, right? Not the worst idea in the world to write a net force statement. If we do a net force statement, I'm going to say that here's T1x, T1y, right? So if net force, let's say in the x, we would have T1x equals NX, all right? And net force in the y, we would have, let's see, NY plus T1y equals mg plus T2. I hope we're okay with me skipping that step where I subtract things and set them equal to 0 and then move the stuff over. So we have a couple of unknowns, right? We don't know what those normal forces are, and we don't know what the tensions are. So therefore, net force sort of leaves us at a dead end. All right, so here's a great opportunity to do net torque equals 0. And a great opportunity here, particularly with the fact that there are two normal forces acting at the hinge there. Let's make that our axis of rotation. All right, so here's our axis of rotation. Okay, let's also pick a positive direction, say this way. Oops, positive. And I'm actually going to get rid of these components now. And I kind of wish I hadn't. Let me put those back in there. T1x, T1y. Okay, so I'm also going to define this as my angle theta. That's that 65 degrees. Okay, the nice thing about putting that axis of rotation there at the bottom where the hinge is we neglect any torque. Well, there is no torque produced by NX and NY. Right? Again, if we say that torque is RF sine theta, well, how about this? Torque is RF perpendicular R is 0 for those N forces. They act at the axis of rotation, so R is 0, no torque. All right. Well, what I'm going to say now is we do our net torque statement. I'm going to say there's a torque from mg, there's a torque from T2, there's a torque from T1. They have to combine to give 0. Hopefully we can see that T2 and mg are both negative. Well, the torques from them. The torque from T1 will be positive. There's our net torque statement. Okay? Let's see. So we want the tension. I'm going to put the tension, well, I'm going to leave it by itself. The torque from tension 1 is equal to the torque from mg plus the torque from T2. Okay? Now, this is what we did in class today. We have to look at components of these forces. I'm going to have to move this a little bit. This is what I would call the component of mg that's perpendicular. And here's mg parallel, and here's mg. And same for T2. Here's what we call T2 perpendicular. Here's T2 parallel because there's T2. Now, the X and Y thing, forget about that, right, when we do torque stuff. I mean, T1 is perpendicular to the boom. So that is the perpendicular component. All right, and now we look for the same angle as our angle theta here. Well, I mean, one way to really sort of do this is say, well, you know, that's a 65-degree angle, that's the fat angle. Where's the fat angle in the triangle? It's here, and it's here. Okay? Okay. The other way to do it is I would say, well, if, you know, here's our right triangle. This is, if here's theta, then this is 90 minus theta, and here's another right triangle, so here's theta again here, right? Okay. So let's see, the torque from T1, well, that's R to T1 times T1 perpendicular. Well, that's just the whole T1. This is R to mg times mg perpendicular. This is R to T2 times T2 perpendicular. Yeah? Let's see. R to T1 is 3L over 4. R to mg is L over 2. By definition, weight force acts at the center of mass. Now, mg perpendicular is mg cos theta. The reason is mg perpendicular is adjacent to this angle, right? Adjacent to the angle. And I know if mg points down and we use cosine, T2 points down, we're going to use cosine also. That acts all the way at the end, so R is the full length L times T2 cos theta. Okay? Now we've got an L in every term. Drop it. And T1 is going to be 4/3 of 1/2 mg cos theta plus T2 cos theta. Where, let's see, M is given, well, mg is given actually, right? So it says a 1200 Newton boom. So mg is 1200. T2 is 2000 because it's a 2,000-pound mass, or sorry, weight hanging from that string. Theta is 65. So if we crank through here, we ought to just make sure we get what we're supposed to get. Let's see. So mg 1200 cosine 65 divided by 2 because it's 1/2 plus T2 2000 cosine 65 times 4 divided by 3. 1.465, or 1465. So yep, 1.47 kilonewtons. Why in kilonewtons? Because someone felt like it. Okay, the components of the reaction force. The components of the reaction force. Well, for that, what I would do is now that we know T, right, I would put that back into here, where T1x is T1, let's see, here's the angle again. If we want to use the same angle theta, there's that angle theta. So T1x is going to be T1, well, it's going to be sine of theta equals nx. And over here, well, ny is, well, mg minus, sorry, plus T2 minus T1y is T1 cosine theta, because it's adjacent, right? Here's T1x, opposite the angle. Here's T1y, adjacent to the angle. Okay, so we can just go right back into net force statements to now find our unknown values of nx and ny. So make sure you can, make sure those work out right. Here are the answers. Okay, so always notice I put this little slide in the notes last time. You'll see we do what do you call it? We do typically a net force statement first, or two net force statements for x and y first. Probably two unknowns there. So go to net torque, right? Once we have, we've found one of the unknowns, we can put that back into the net force statements to find our other unknown. Okay? Yeah, these are tricky. I mean, what's the tricky part? The tricky part, I will tell you, people forget. Let me do this. If we go back to this problem, it went the other way, right? Here's the boom, and here's like mg, and here's our axis of rotation. People will do this. Okay, torque is r f perpendicular. Here's right mg perpendicular. Keep doing this. Here's mg parallel. Here's mg, right? Perpendicular to the boom. Or really perpendicular, I mean, the important part is that it's perpendicular to vector r. There's vector r. All right, let's see. And if this is angle theta, if this is angle theta, then let's see, this is angle theta. The big thing people will goof up here is they'll say, they'll do r, I mean, I write it like this, r to mg times mg perpendicular. Just make sure you know that this is just, a subscript. That's just notation. And this is the force, really the perpendicular component of the force. So a lot of people will forget to include this part. They'll forget to do the r part, right? So torque in this case is L over 2, right? That's the actual vector r, or the magnitude of vector r that goes from the axis, in this case, to the center of mass, right? Times the force, mg perpendicular, right? And for sure, the hard part, or the, a significantly tricky part is to take care of this, right? Gee, the perpendicular part, how many of you had problems saying, oh yeah, I understand that this is where, theta is, if this is angle theta. That's tricky. It's not physics, right? It's geometry. But, that can certainly be tricky. So this would be, in this case, mg cosine theta. All right? And, here's something we said in class. I just want to make a note of it. So all up and down f perpendiculars will use the same trig function. Right? In this case, any other, notice if we go to this solution, notice T2 and mg were both downward forces. Notice we used cosine for both of them. No coincidence, right? And I'll say, therefore, all side-to-side forces. I don't like this notation. I'll just say F's. Yeah. All side-to-side F's will use the other trig function. Okay? So, right, since mg, the force that produces a torque, let's go back here. Since mg, the force that produces a torque, is downward, and T2, a force that produces a torque, is downward, they both use cosine of theta. If there was a vertical force, like there was in our ladder example, sorry, if there's a horizontal force, like there was in our ladder leaning against a wall example, that a normal where the ladder hits the wall. Let's say, well, yeah, sure. Let's do this. Let's say this thing is leaning against a wall, right? Well, there's a normal force here. The torque from that normal force. I'm not even going to draw the triangle and all the angles. I'm just going to say I know if a vertical force uses cosine, then this torque from the normal would have to be, well, r to the normal, which is the full length L, times n sine theta. I just know it is. We can prove it by drawing it. I will. But right, if a downward force, a vertical force, uses cosine to find its perpendicular component, a horizontal force, like this normal force, has to use the other trig function. All right, so let's just prove that. All right, so there's normal, n perpendicular. I made n too long. Here's n. N perpendicular looks like this. Here's n parallel. And let's see. So the angle, right, we can go opposite interior angles. Here's this one, here's this one. Same angle? No, not true, not true. Right? Not true. Undo. So let's see. Yeah, well, let's see. Here, okay. So here's angle theta, here's angle theta. That's opposite interior stuff, right? This is a right angle. Oh yeah, so here's another opposite interior. So there is the angle theta. And n perpendicular, like we said, check it out. N perpendicular is opposite that angle. Okay, hence we use sine over here. All right? So, I mean, I said the other day that there are a bunch of these problems. Torque problems are ones that I haven't been solving for too long since I got out of college. So a 15-year, break I had in those. So, each year kind of leads me back to figuring out how to solve them again. So what I'm sort of trying to do is come up with some general tricks, that seem to work. And this one definitely works. All right. If you can figure out one of them, and what I mean is, do I use cosine or sine? Right. Literally, if one of the forces you say, okay, I know for this one the perpendicular component has to involve cosine. Well, then, boom, apply this rule. Every other force that points in the same direction that one does uses the same trig function. Every force that points in the other direction, the perpendicular direction to that, has to use the other trig function. That can help, I guarantee it. All right, unless it's just my thinking that no one thinks the same way, but I can't imagine that's true. Okay, folks, I will see you tomorrow. All right, and believe me, I know these homework problems will be hard. All right, I'd like you to try to work through them. At the very least, you need to have, when you come in tomorrow, you need to have free body diagrams drawn for all of them. Do not try to draw them on the handout that I gave you. There's not enough space. All right, you should probably have a whole page for each one of these problems, just to give yourself enough room to draw a nice big free body diagram. I guarantee a nice big free body diagram will make your life a ton easier. Notice how I draw mine here, right? Instead of drawing, here's the boom, and okay, MG looks like there's MG, right? Then I have to do, I saw a bunch of this in class, little tiny things like this. Here's a normal, there's the perpendiculars, and then I don't know which angle's which. It's so hard to tell. right? If you draw these forces like I've drawn them, nice and big, right, nice and long, it can be a lot easier to tell where the angles are. All right, so for sure, you need free body diagrams for everything. You should, without any problem at all, be able to write net force statements, right? Net force equals 0 statements for all of these things, right? If you can get to a net torque statement and figure out which ones are positive and negative, that's great. If you can get into this step here, saying, well, I know how to calculate torque, it's R times F perpendicular, that's great. So, just try to take it step by step, folks. Believe me, I know they're going to be challenging. Right? There will be some where people say, I don't know where to start, but you know where to start. It's a free body diagram. You know what to do next. It's a net force statement. Ideally, you know what to do next. It's a net torque statement. So do the best you can. We'll have a good amount of time tomorrow to work through them. Okay? All right, folks. Adios.